Listen, every single day, light is traveling across the universe at precisely 299,792,458 meters per second. And you probably never stop to wonder what that actually means. You hear people say it's the cosmic speed limit, the fastest anything can go, but that explanation is worthless. That's not an answer. That's just repeating what you've been told. The real question, the question almost nobody asks, is this: what physically prevents anything from going faster? Not what Einstein said, not what the textbooks claim, but what mechanism in reality itself creates this barrier. When you actually dig into this, when you strip away the surface level explanations and look at what's really happening, you find something so profoundly weird that it demolishes your entire intuition about how the universe works. The speed of light isn't a speed limit like a highway sign. It's the underlying architecture of reality. Space and time are literally constructed around this value. And once you see how, you can never look at the universe the same way again. Let me take you back to something basic, something you understand without thinking about it. Drop an object, any object, it falls. Galileo measured this precisely. Things fall 16 feet in the first second. Drop a ball, drop a rock, drop your phone, doesn't matter, 16 feet in 1 second near Earth's surface. Now look up at the moon. The moon isn't falling, right? It's just sitting up there, orbiting around the Earth in a nice circle. Except that's completely wrong. The moon is absolutely falling. Every single second, the moon is falling toward Earth. Think about what would happen if the moon suddenly stopped moving sideways, if it just froze in its orbit and hung there motionless in space. What would happen? Gravity would pull it straight down toward Earth. It would fall, but the moon isn't motionless. It's moving sideways, tangent to its orbit, moving fast enough that as gravity pulls it downward, it keeps missing the Earth. It falls toward the Earth, but the curvature of its path makes it continuously miss. That's what an orbit actually is. Perpetual falling combined with sideways motion. The moon is in constant free fall around our planet. Newton saw this and had one of those insights that changes everything. He looked at the moon 240,000 miles from Earth's center and compared that to us standing on the surface, 4,000 miles from Earth's center. The moon is 60 times farther away than we are. And Newton asked himself, what if gravity weakens with distance? Not just weakens, but weakens according to a specific mathematical relationship. What if gravity follows an inverse square law? Meaning if you double the distance, gravity becomes 4 times weaker. Triple the distance, 9 times weaker. The weakening goes with the square of the distance. If that's true, then at the moon's distance, being 60 times farther away, gravity should be 60 squared times weaker. That's 600 times weaker than the gravity we feel standing on Earth's surface. So Newton did the calculation. On Earth, objects fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth at a rate 3,600 times slower. Take 16 feet divided by 3,600. You get about 1/20th of an inch per second squared. Newton calculated exactly how far the moon should fall toward Earth every second if his inverse square law was correct. And then he compared it to the actual motion of the moon, measured from its orbital period and distance. They matched perfectly. The moon falls toward Earth at exactly the rate Newton's law predicts. This wasn't just a lucky guess. This was connecting 2 completely independent observations. How fast things fall on Earth, which had been measured for decades, and the motion of the moon, which had been tracked for centuries. 2 totally separate phenomena, suddenly unified by one mathematical law, the law of universal gravitation. But Newton didn't stop there. He took his law and calculated what shape a planetary orbit should be if gravity follows this inverse square relationship. The mathematics gave him an ellipse. And what shape do planets actually follow? Ellipses. Kepler had already measured this decades earlier, painstakingly tracking Mars and the other planets, discovering that they move in elliptical orbits with the sun at one focus. But Kepler had no idea why. He just knew it was true from observation. Newton explained it. The inverse square law of gravity produces elliptical orbits. One law explained both why things fall and why planets orbit the way they do. Two phenomena for the price of one equation. Then there were the tides. For thousands of years, people knew the tides were connected to the moon. When the moon is overhead, the tide is high. But here's the puzzle. There are 2 high tides per day, not one. If the moon just pulls the ocean toward it, you'd expect one bulge of water on the side facing the moon. 1 high tide per day, but we get 2, roughly every 12 hours. Why? People proposed all kinds of explanations. Some said the earth gets pulled away from the water. Others said the water gets pulled toward the moon. Both ideas had elements of truth, but neither quite worked. Newton figured it out. The key is that gravity gets weaker with distance. The water on the side of Earth facing the moon is closer to the moon than the center of the Earth is, so it experiences stronger gravity pulling toward the moon. It gets pulled more. The water on the opposite side of Earth is farther from the moon than Earth's center, so it experiences weaker gravity. It gets pulled less. The Earth itself is pulled with a force somewhere in between, so you get 2 bulges. One where the water is pulled more strongly toward the moon than the Earth is, creating a bulge on the near side, and one where the Earth is pulled more strongly than the water on the far side, so that water gets left behind, creating a bulge on the far side. 2 high tides per day. The mathematics of gravity explained an observation that had puzzled humanity for millennia. Everything started falling into place. Why is Earth round? Because gravity pulls everything inward toward the center with equal force in all directions. Why isn't it perfectly round? Because it's spinning, and the rotation throws material outward at the equator just enough to create a slight bulge that balances against gravity. Why are the sun and moon round? Same reason. Gravity pulling inward, creating spheres. The law of gravitation explained the shapes of celestial bodies, the motion of planets, the tides, falling objects, everything. As science progressed and instruments improved, the tests of Newton's law became incredibly precise. One of the first serious tests involved the moons of Jupiter. Astronomers carefully observed Jupiter's moons over long periods, tracking their orbits with increasing accuracy. And they found something disturbing. The moons weren't following Newton's law exactly. Sometimes they appeared 8 minutes ahead of schedule, sometimes 8 minutes behind. 8 minutes is huge. That's not a small measurement error. Something was seriously wrong, either with the observations or with Newton's law of gravity. But then someone noticed a pattern. The moons appeared ahead of schedule when Jupiter was close to Earth, behind schedule when Jupiter was far from Earth. That's a very specific pattern, not random error. A scientist named Rømer, having complete confidence in Newton's law of gravitation, came to a shocking conclusion. The discrepancy wasn't because Newton's law was wrong. It was because light takes time to travel. When we look at Jupiter's moons, we're not seeing them as they are right now. We're seeing them as they were some time ago, the time it took for light to travel from Jupiter to Earth. When Jupiter is closer to Earth, light takes less time to reach us. When Jupiter is farther away, light takes longer. The moons appeared ahead or behind schedule because we were seeing them at different delays depending on Earth's distance from Jupiter. By measuring how much the moons appeared to be ahead or behind schedule, and knowing the distances involved, Rømer calculated the speed of light. This was the first demonstration in human history that light doesn't travel instantaneously. It has a finite speed. Stop and think about what just happened there. We discovered the speed of light not by measuring light directly, not by timing light beams, but by having such confidence in the law of gravitation that when something didn't match, instead of throwing out Newton's law, Rømer said there must be another phenomenon at work. And he was right. Light has a travel time. This is how science progresses. When one law is firmly established, you can use it to discover other laws. Each discovery provides tools for more discoveries. This is the avalanche Newton started, and it's been accelerating for 400 years, and we're still avalanching along right now. Once you know light has a finite speed, once you can measure that speed accurately, you start noticing something absolutely bizarre. Light always travels at the same speed. Always. It doesn't matter who's measuring it. It doesn't matter how fast you're moving. The speed of light is always exactly the same. Let me make this concrete, because this is where your intuition is going to fail you completely. You're standing still on the ground. You turn on a flashlight. You measure the speed of the light coming out of that flashlight. You get 299,792,458 meters per second. Fine. That's the speed of light. Now imagine you get on a train, a very fast train, moving at half the speed of light. You're on this train holding the same flashlight. You point it forward in the direction the train is moving, and you turn it on. Common sense, everyday experience, everything you know about how speeds work tells you that the light should now be moving faster. The light is moving at the speed of light, plus the train is moving at half the speed of light. So the light should be moving at 1.5 times the speed of light relative to the ground. That's how speeds add. If you're on a train moving 50 miles per hour and you throw a ball forward at 20 miles per hour, the ball is moving 70 miles per hour relative to the ground. Speeds add. That's basic. Except with light, they don't. You measure the speed of that light beam coming out of your flashlight while you're on the train moving at half the speed of light. You measure the light. It's still moving at 299,792,458 meters per second. Exactly the same speed. Not faster. Not the speed of light plus the speed of the train. Just the speed of light. You think you made a mistake. You check your instruments. You measure again. Still the same. You say, fine, maybe half the speed of light isn't fast enough to see the effect. So you get the train going faster, 90% the speed of light. You shine the flashlight forward. You measure the light. Still 299,792,458 meters per second. Same speed. You're frustrated now. This makes no sense. You push the train even faster, 99.9999% the speed of light. You're moving almost as fast as light itself. You shine the flashlight forward, you measure, still the exact same speed, 299,792,458 meters per second. This should shatter everything you think you know about motion. Speeds are supposed to add. That's how motion works. If you're moving and you throw something forward, it moves faster than if you threw it while standing still. But light doesn't do this. Light doesn't care how fast you're moving. It always moves at the same speed relative to you. Always. No matter what. You cannot make light go faster by moving faster yourself. The speed of light is the same for everyone, regardless of their motion. This is not intuitive. This is not how anything else in the universe behaves, and yet it's absolutely, undeniably true. Every experiment ever done confirms it. Einstein realized what was actually happening, and the answer is so strange that even over a century later, most people cannot truly accept it. Time and space are not fixed. They're not rigid. They're flexible. They bend and stretch and compress to keep the speed of light constant for everyone. When you move faster, time literally slows down for you. Your clock ticks slower, not because there's something wrong with your clock, but because time itself is passing more slowly for you. And distances change. The space in front of you contracts, compresses. Objects get shorter in the direction you're moving. These are not optical illusions. These are not tricks of perception. These are not measurement errors. Time actually slows. Space actually contracts. These effects are real physical changes in the structure of space-time itself. And the amount time slows and space contracts is precisely, mathematically, exactly the amount needed to make the speed of light come out the same for you as for someone standing still. The universe adjusts time and space, warps them, bends them to ensure that no matter how fast you're moving, when you measure the speed of light, you always get the same answer. The speed of light isn't just some speed that happens to be constant. The constancy of the speed of light is a structural feature of the universe. Space and time are woven together in such a way that this speed must be the same for everyone. That's the universe we live in. Now here's where it gets even more extreme. If you try to accelerate something with mass to the speed of light, something very strange happens. The closer you get to the speed of light, the harder it becomes to go faster. And this isn't a matter of needing a more powerful engine. It's not that you run out of fuel. It's that the object itself resists acceleration more and more as it approaches light speed. We describe this as relativistic mass increase, though that's a bit of a misnomer. What's really happening is that the object's inertia increases. It becomes harder and harder to change its velocity. And as you approach the speed of light, the resistance approaches infinity. To actually reach the speed of light with an object that has mass, you would need infinite energy, which is impossible. Infinite energy doesn't exist. You can't get it. So nothing with mass can ever reach the speed of light. Not because of some arbitrary rule imposed on the universe. Not because we haven't built a powerful enough rocket, but because the fundamental structure of space-time itself prevents it. Light can travel at that speed because photons, the particles of light, have zero mass. Massless particles travel at the speed of light. They have to. They have no other option. A photon is always moving at light speed from the moment it's created until the moment it's absorbed. It never speeds up, never slows down, always exactly the speed of light. But anything with mass, even a tiny amount of mass, can never reach that speed. You can get close, incredibly close. In particle accelerators, we routinely accelerate particles to 99.9999% the speed of light, but never quite to the speed of light itself. The universe won't allow it. You might ask why. Why is the universe set up this way? Why is there a maximum speed at all? And here's the answer that most people find unsatisfying, but it's the truth. There isn't a deeper why in the sense you're looking for. The speed of light being a maximum isn't some arbitrary speed limit imposed on the universe like a law passed by cosmic legislators. It's a consequence of how space-time is fundamentally structured. Space and time aren't separate, independent things. They're unified into a single four-dimensional structure called space-time. And space-time has geometry, it has structure. And that structure includes a built-in conversion factor between space and time. That conversion factor is the speed of light. It's not that light is special. Light just happens to travel at this speed because photons have no mass. But the speed itself, that maximum rate, is a property of space-time, not a property of light. If light didn't exist, if photons weren't a thing, the maximum speed would still be there. It's a feature of space-time itself. Space-time has a maximum rate at which cause and effect can propagate, a maximum rate at which information can travel, a maximum rate at which anything can happen. Light travels at that rate, but the rate exists independent of light. Here's another way to think about it that might make it clearer. In everyday experience, you think of space and time as completely separate. You move through space. Time passes, they're independent dimensions, but that's wrong. You're always moving through space-time at a constant rate, always. But your motion through space-time is divided between motion through space and motion through time. If you're sitting perfectly still, not moving through space at all of your motion is through time. You're moving into the future at the maximum rate, 1 second per second. But if you start moving through space, you have to divert some of your motion away from the time dimension. You're now moving through space, which means you're moving through time more slowly. Your motion through space-time is conserved. The faster you move through space, the slower you move through time. And there's a maximum to this. If you could move through space at the speed of light, you would be using all of your motion through space-time for spatial movement. You would have zero motion left for temporal movement. Time would stop for you completely. This is why photons don't experience time. From a photon's perspective, if a photon could have a perspective, it's emitted from a star and absorbed by your eye in the same instant. Zero time passes for the photon. The photon's entire existence, from creation to destruction, happens in a single moment from its reference frame. The universe is frozen. You can't go faster than light because you can't have less than zero motion through time. You can't move backwards through time. That's the limit. That's the wall you hit. The speed of light is the speed at which all your motion through space-time is devoted to spatial motion, leaving none for temporal motion. You can't go faster because there's nothing left to divert. You've used up all your motion through space-time. That's why it's a maximum. That's why nothing can go faster. And this isn't just theoretical philosophy. This isn't just mathematical abstraction. We've tested this over and over with extraordinary precision. In particle accelerators around the world, we accelerate subatomic particles to incredibly high speeds. Electrons, protons, heavy ions, all accelerated to significant fractions of light speed. And the closer they get to light speed, the harder it becomes to accelerate them further, exactly as Einstein's equations predict. The energy required increases asymptotically. You can pump more and more energy into the particle, and it gets closer and closer to light speed, but never reaches it. The measurements match the theory to absurd precision. GPS satellites have to account for relativistic time dilation. The satellites are moving at high speeds relative to us on the ground, and they're also in a weaker gravitational field. Both of these effects cause time to pass at a different rate for the satellites than for us. If we didn't correct for relativistic time dilation, if we just assumed time passes at the same rate everywhere, GPS would accumulate errors of several miles per day. The system would be useless. But we do correct for it using Einstein's equations, and GPS works perfectly. Every single time you use GPS, you're relying on the reality of time dilation. Cosmic ray muons are another beautiful confirmation. Muons are subatomic particles, similar to electrons but heavier. They're unstable and decay very quickly. A muon at rest lives for about 2 microseconds before decaying. Cosmic rays hitting the upper atmosphere create muons about 10 kilometers up. Those muons travel toward Earth's surface at close to the speed of light. But here's the problem. Even at light speed, it takes about 33 microseconds for something to travel 10 kilometers. The muons should decay long before reaching the ground. They only live 2 microseconds. By the time they've traveled even a fraction of the distance to the surface, they should be gone. And yet we detect huge numbers of muons at ground level. Why? Time dilation. The muons are moving at 99.9% the speed of light relative to us. From our perspective, time is passing much more slowly for the muons. Their 2 microsecond lifespan is stretched out to much longer in our reference frame, long enough for them to reach the ground before decaying. From the muon's perspective, it's different. From the muon's reference frame, time passes normally for the muon, but the distance to the ground is contracted. The atmosphere is compressed. Instead of traveling 10 kilometers, the muon only has to travel maybe a few hundred meters because of length contraction. Either way you look at it, from our frame or the muon's frame, more muons reach the ground than classical physics would predict. And the number that reaches the ground matches Einstein's predictions exactly. This is measured. This is experimental fact. The speed of light being a cosmic limit is not speculation. It's not philosophy. It's one of the most thoroughly tested principles in all of physics. Every single experiment, every observation, every measurement confirms it. We've never found an exception. We've never found anything that violates it. It's as solid as the fact that things fall when you drop them. So let's pull all of this together. Why is the speed of light the ultimate speed limit? Because space-time, the four-dimensional structure that makes up our universe, has a maximum rate at which causality can propagate. That maximum rate is what we call the speed of light. Not because light is fundamentally special, but because space-time itself has this built-in conversion factor between space and time. You can't go faster than light because going faster would require moving backwards in time, which violates causality. Cause comes before effect. That's built into the structure of space-time. The speed of light is the speed at which now propagates through the universe. It's the speed at which information travels. It's the speed at which forces act across distance. It's the maximum rate of change possible. And look at how we got here. Newton figured out gravity by watching the moon fall around the Earth. Rømer figured out the speed of light by watching Jupiter's moons and trusting Newton's law. Einstein realized the speed of light must be constant and derived relativity from that single insight. Then thousands upon thousands of experiments confirmed every prediction relativity makes. Each discovery built on the previous ones. Each new insight opened doors to more insights. That's the avalanche Newton started 400 years ago. That's how science works. Not by guessing, not by philosophy, but by building layer upon layer of tested, confirmed, predictive understanding. The speed of light isn't just a number in a textbook. It's not just the fastest speed. It's the key that unlocks how space and time actually work. It's the thing that reveals the universe is far stranger, far more beautiful, far more elegant than our everyday intuition could ever suggest. And the fact that we can understand this, that we can measure it, test it, predict with it, use it to build technologies that work, that's the power of physics. Not to make you comfortable, not to confirm what you already believed, but to show you the truth about reality, no matter how strange that truth turns out to be. The long night had passed, but the world did not awaken. The living clung to survival while the dead still moved beneath the snow. Old enemies faced a greater terror. Fear forced choices once thought impossible. Winter did not loosen its grip, it tightened it, and the war for survival had only just begun.